From space, it's a colossal white expanse at the bottom of the world, Antarctica, the coldest, driest, windiest, and highest continent on Earth. For most of history, we saw it as a featureless cap of ice, a static, frozen desert. But that perception of a placid, dormant continent is a grand illusion. Beneath an ice sheet kilometers thick lies a hidden world of staggering scale and dynamism. A realm of towering mountains, vast canyons, and liquid lakes that has been shielded from sight and sun for millions of years. This isn't science fiction. This is a journey into the last great wilderness on Earth, an exploration of the subglacial worlds hidden beneath the ice. The first clues were speculative. In the 1960s, pilots flying over the interior reported unnervingly flat areas in the ice, calling them lakes. At the same time, glaciologists calculated that the immense pressure of the ice, combined with geothermal heat from the Earth's crust, could theoretically keep water liquid at the base of the ice sheet. But these ideas remained theory until the advent of a technology that would revolutionize polar science: ice-penetrating radar. The principle is simple. An aircraft flies over the ice, sending pulses of radio waves downward. The ice is transparent to these waves, so they pass right through until they hit a boundary, like the bedrock below or a layer of liquid water. The waves reflect back to the aircraft. By measuring the echo's return time, scientists can calculate the ice thickness with incredible precision. But the echoes contain more information than just depth. A strong, bright, mirror-like reflection indicates a flat, smooth surface, the kind formed by liquid water. A scattered, uneven echo suggests rough, rocky terrain. Suddenly, we had a way to see through the ice. Combined with seismic surveys and incredibly precise satellite measurements of the ice surface, the scientific community was poised to map an entirely new continent, one hidden beneath a veil of white. One of the first and most enigmatic discoveries was a phantom mountain range deep in the heart of East Antarctica. During the International Geophysical Year in 1958, a Soviet expedition detected a massive subglacial highland using seismic soundings. They named it the Gamburtsev Subglacial Mountains. The discovery was a profound puzzle. The mountains were comparable in size to the European Alps, with sharp, rugged peaks estimated to reach 700 meters, features typical of a much younger range. But they were located in the middle of an ancient, tectonically stable part of the continent. Major mountain ranges are formed by colliding tectonic plates, but nothing like that was happening here. How could such a massive, youthful-looking mountain range exist in the heart of an old craton? The mystery of these ghost mountains, buried under up to 3 kilometers of ice, persisted for decades. The answer, finally pieced together by a major international effort during the International Polar Year of 2007 to 2009, revealed a geological story of epic proportions. Using aircraft equipped with advanced radar, scientists mapped the hidden range in stunning detail. The Gamburtsev story began 1 billion years ago, during the formation of the supercontinent Rodinia. A collision between two plates forged an initial mountain range, leaving behind a thick, dense crustal root that extended deep into the Earth's mantle. Over hundreds of millions of years, those ancient mountains were completely eroded away, but the cold, deep root remained. Then, between 250 and 100 million years ago, as the supercontinent Gondwana began to break apart, the crust near this ancient root started to stretch and rift. This process warmed and rejuvenated the dormant root, giving it the buoyancy to lift the land upwards once more. A new mountain range was born. Rivers and later alpine glaciers carved deep, sharp valleys into this uplifted plateau, sculpting the jagged peaks we see today. The final act was preservation. Around 34 million years ago, as global temperatures plummeted, glaciers began to form in the highlands of the newly reformed Gamburtsevs. This was the genesis of the colossal East Antarctic ice sheet. The growing ice sheet expanded with astonishing speed, effectively flash freezing the alpine landscape and protecting it from further erosion. The Gamburtsev Mountains, Once a cradle of glaciers, became entombed by their own progeny. They were the primary birthplace of the largest ice sheet on Earth. As mapping improved, an even more ancient world began to emerge. Scientists found that Antarctica's warmer past was etched into the bedrock in the form of vast, preserved river systems. Recent studies have uncovered extensive landscapes shaped by rivers at least 14 million years ago, and possibly even before the Great Glaciation 34 million years ago. These aren't small streams but continent-spanning drainage basins. One study identified a 32,000 square kilometer area of ancient valleys and ridges, a terrain strikingly similar to the glacially modified landscapes of North Wales. These findings paint a vivid picture of a very different Antarctica. Before the ice, it was part of a temperate supercontinent, covered in dense forests with a vast network of rivers carving their way to the sea. The remarkable preservation of these river-carved plains suggests the ice sheet formed rapidly and, in many areas, froze to the bed, acting as a protective shield rather than an erosive force. This ancient topography has a profound influence on the present. The deep troughs carved by these prehistoric rivers now act as channels for some of Antarctica's largest and fastest-flowing glaciers, guiding ice from the interior towards the ocean. Adding another layer of complexity is active volcanism. West Antarctica is one of the most extensive volcanic provinces on Earth. In 2017, researchers identified 91 previously unknown volcanoes buried beneath the ice sheet, some rising to nearly 4,000 meters. This volcanic activity provides a significant source of geothermal heat, melting the base of the ice sheet and contributing to the formation of subglacial lakes. This interplay between volcanic heat and overlying ice is a critical factor in the stability of the entire West Antarctic ice sheet. The combination of geothermal heat from below and the immense insulating pressure of the ice from above creates one of the most astonishing features of the subglacial world: liquid water. Beneath the Antarctic ice sheet lies the largest wetland on our planet, an enormous, interconnected system of rivers and lakes. To date, over 400 subglacial lakes have been discovered. The crown jewel of this hidden hydrological system is Lake Vostok. Buried beneath nearly 4 kilometers of solid ice, Lake Vostok is one of the largest lakes in the world, roughly the size of North America's Lake Ontario. Its existence was confirmed in the 1990s, and it immediately ignited the scientific community. Here was a body of water completely isolated from Earth's atmosphere and sunlight for an estimated 15 million years. It represented a potential time capsule, its waters holding an undisturbed record of ancient climate. And it posed a tantalizing question: could life exist in such an extreme environment of perpetual darkness, immense pressure, and frigid temperatures? This question drove one of the most ambitious drilling projects ever undertaken. For 2 decades, Russian scientists at Vostok Station painstakingly drilled through the overlying ice. The project was fraught with challenges, not least the fear of contaminating the pristine lake with drilling fluids. Finally, in February 2012, the drill bit breached the ice sheet and entered the lake. Initial analyses of frozen lake water retrieved from the borehole were contentious, with concerns about contamination making the results ambiguous. But the attempt proved that vast, liquid water environments were a fundamental feature of the continent. The challenges at Vostok spurred the development of clean drilling technologies designed to melt through the ice without introducing any surface microbes. The most successful of these is the hot water drill, which uses a jet of scalding, sterilized water, filtered and treated to be cleaner than a hospital operating room. This technology paved the way for the WISS ARD project, an American-led mission to be the first to cleanly sample a subglacial lake. Their target was Lake Whillans, a smaller, shallower lake beneath 800 meters of ice in West Antarctica. In January 2013, the team successfully drilled into Lake Whillans. The samples they retrieved provided the first definitive proof of a thriving ecosystem in a subglacial lake. The dark, cold waters were not sterile, they were alive. Subsequent analysis revealed a diverse community of nearly 4,000 species of microbes. So how does life survive in a world without sunlight? The answer is chemosynthesis. Instead of photosynthesis, the microbes of Lake Whillans derive their energy from chemical reactions, essentially eating the minerals and chemical compounds found in the water and ancient marine sediments at the lake bottom. The most abundant organisms were archaea that oxidize ammonium for energy. Others metabolize iron and sulfur. In essence, they are rock eaters, opportunists that evolved to utilize every scrap of chemical energy in their cold, dark world. This showed that life could flourish in one of the most extreme environments on our planet. This discovery has profound implications that extend far beyond Earth. For astrobiologists, Antarctica's subglacial lakes are our planet's closest analogs to the subsurface oceans believed to exist on Jupiter's moon Europa and Saturn's moon Enceladus. These alien oceans are considered some of the most promising places to search for extraterrestrial life. The conditions are strikingly similar. A liquid water ocean in contact with a rocky core, sealed off by a thick ice shell, with no sunlight but with potential energy from hydrothermal vents or chemical reactions. Before Antarctica, the idea of life in such a place was pure theory. Now, we have a proof of concept. The fact that entire ecosystems can sustain themselves by eating rocks in perpetual darkness strengthens the case that life could persist in the hidden oceans of other worlds. The world beneath the ice is not a static museum piece. It is an active component of the Earth system that impacts our entire planet. The subglacial topography, the mountains and ancient river valleys, steers the flow of ice. The extensive network of subglacial water acts as a lubricant, reducing friction and allowing ice to slide more easily. The draining of large lakes can cause glaciers to suddenly accelerate. Understanding these processes is critical for predicting the future of our climate and sea levels, as the stability of the West Antarctic ice sheet is a major factor in how much our oceans will rise. The story of subglacial discovery has transformed our vision of Antarctica. The image of a static, lifeless continent has been shattered, replaced by a dynamic reality. We now know that beneath the ice lies a ghost continent of mountains and canyons preserved from a bygone geological era. We have discovered a lost world of water, a vast network of lakes and rivers that harbor unique ecosystems, alive in the crushing darkness. This journey of discovery is a testament to human ingenuity. By peering through kilometers of solid ice, scientists have not only mapped a new frontier on our own planet, but have also found a mirror reflecting the possibilities of life on distant, icy worlds. Antarctica, the white continent, is slowly unveiling its true face, reminding us that our planet still holds profound and breathtaking secrets waiting to be discovered.